Yeah, so this is a talk about geometric dissections, and we'll start with polygons and maybe get into some other stuff. So first I want to say that actually it turned out that basically like a lot of this talk came from this book, which turned out to be very helpful. It's like kind of like an authoritative book about dissections of all sorts, and it's right there if anybody wants to take a look at it. But a geometric dissection between two shapes is just a way to cut the first shape into some pieces, which can be rearranged to form the second shape. And because it's kind of a recreational math sort of thing, or it has been a recreational math sort of thing for most of its history, there's a lot of like trying to find the most symmetric one, or the one that's most aesthetically pleasing, or ones with some other properties that we'll talk about later. But in particular, also with the fewest pieces. So for example, here's one that I found. There's an app called GeoGebra, which has like a lot of pretty cool demonstrations. And so this is like, you have some pentagon, and can you dissect it to make a square? Well, one way to do it is to cut it in all these random places, and then here, and then you can rearrange the pieces like this, and you get a square. So super easy.
Do you have to use all the pieces?
Yeah, you have to use all the pieces. That's right.
Okay.
So because of that, it has to be the same area. Because if you didn't have to use all the pieces, you could kind of like, you could like cut out a little square in here, then throw the rest of it away. But you can't do that, so it has to be the same area square as the thing you started with. And this is good, and you can actually like find a whole ton of these things. If you like read the description, there's, I guess, this problem from Dudeny, from equilateral triangle to square, and we were just talking with Tom about how would you ever come up with such a thing. And it's yeah, it's like not it's like not a science. It's like an art. Like if you like look at people who like came up with these things, they have all sorts of little tricks and all sorts of like tactics and strategies to do this. But there are a few general methods, some of which have like just emerged in the 20th century that allow people to do these things. And I'll tell you these methods, and then I'll give you a little example of how they work. So the first method is called overlaying tessellations. And the description from the book there is the way that you work this is you create two tessellations of the things that you want to dissect. You overlay them, and then you allow the line segments in one to induce cuts in the figure of the other. And so let me tell you how that's supposed to work. At least I don't find it so obvious. Let's see here. So if we start with a problem of dividing a square into 5 equal smaller squares, we can do that with this method. And I picked this problem because squares is very easy to find a tessellation. So let's see here. Okay, so here's one tessellation of squares. And here's another. And so the idea is we want to overlay these two on top of each other so that they have the same repetition pattern, and so that we can allow one to induce cuts in the other one to kind of get the dissection we want. So if we overlay them like this, and then let me just actually focus on, for example, one square here. Let me actually size this. We've sized up the larger tessellation so that the squares are 5 times as big as the smaller one. And because we can overlay them on top of each other so that, for example, the pattern inside here is the same as the pattern inside here, which is the same as the pattern inside here, and so forth, this actually induces a dissection of the five squares into one square. And just to be explicit about how that works, you start with your one square here, and you dissect it into these 9 pieces, this triangle, this weird shape, this triangle, these 3 pieces. And then you can form 5 squares from that by hinging this one, rotating this one over here to create 1 square, rotating this one over here to create a square, rotating this one over here to create a square, and rotating this one over here to create a square. And that gives you these 4 squares and this 5th one in the middle. I'm not sure if that was a good or bad explanation. Does anyone have any questions about that? Or do you want to stare at this for longer?
Excuse me. Question. You divide here is it should be in the intersection all the time because they're not so not in the intersection.
What do you mean by the intersection?
No. You see all these lines.
Oh, yeah.
Blue and green should be at one point here and there.
Yes,
and
that's
here,
right, yeah.
Because it's not perfect.
Yes, you're right. It's not perfect. That's right.
It should be
But they
perfect,
should,
yes.
yeah, all these green points should
Okay.
intersect the blue grid in the,
Yes.
yeah, thank you for
I
clarifying that.
understand.
Yeah.
Thanks.
While you're looking at this, I'll tell you, so this is, I actually don't know how to pronounce his name, but this was, I think, first come up with by an Arabic mathematician named Abul Wafa, who generalizes. So there's actually like a full method whereby you can dissect 1 square into any number of squares as long as that number of squares is the sum of 2 squares. So 5 is 1 plus 2 squared. So you can dissect this square into 5 squares. And you can also, I mean, you wouldn't think of this as like a very difficult thing, but you can also use this same method to, for example, dissect 1 square into 2 squares. Like,
Michael, excuse me, you said Arabic, was this one of these like in the Middle Age Arabic?
yeah, I think it's around the 10th century, something like that. Yeah, sorry.
Way back-
Yes,
way
that's
back,
right. Yeah.
one of those, okay.
They'd had like a lot of talk about dissections when they were writing some commentary on Euclid and things like this. And actually, it'll come up again later. But so, for example, you wouldn't need a special method to do this, but you can do it like this, and you get a dissection of 1 square into 2 squares, because 1 is 1 square. 2 is 1 square plus 1 squared. So you can do this 1 square into any number of smaller squares, as long as that number is the sum of 2 squares. Any questions? Okay. Okay, so, oh, right, okay. So, yeah, so you can actually generalize this slightly to just give a dissection of any 2 given squares, which may be unequal, don't have to be, into 1 square. And so let me do this here. So let's take, oops. I guess this is 2 square-like things. And so any 2 squares, it turns out, if you put them together, they will tile the plane in a regular tessellation, which you can either see in your mind if you are not me, or you can just kind of do it. They sort of nestle in like this. And then you can create a tessellation by connecting, for example, this lower corner of all the larger squares, or any point which is the same on the entire pattern. So you can do, let me do this in blue. This is not going to be perfect, as warning. So this gives, and then if you then again, for example, focus in on this square here, oh, whoops, sorry. Well, if you focus in on this square here, you can see how to dissect it into 1, 2, 3, 4 pieces, which then can be rearranged to give you the to give you the two unequal squares. And this was actually not by this method. This was discovered in the 1800s. Sorry, actually, so you can make the tessellation happen whatever. So you can, for example, move it around. And so this one's actually maybe some people might consider a little bit more aesthetically pleasing because you have this rotationally symmetric thing around here. So you have one square here and then four of the same piece, which can be rearranged to make the two unequal squares. And a guy, an amateur mathematician in the 1800s called Perigol, came up with this particular dissection. And he thought of it as actually a proof of the Pythagorean theorem. It's actually not clear, at least when I read that, I was like, it's not clear how this diagram proves the Pythagorean theorem. And according to Wikipedia, it's a little bit convoluted to actually make that rigorous. But at least it's like an actual dissection, which is correct.
Well, there's a similar proof that looks almost like that, except the four corner pieces are triangles.
Yeah, there's...
You know that one, that's probably...
Yeah, there's various diagrams which look like this, which are used in proofs of the Pythagorean theorem. But it's not clear.
Yeah.
I think the pictures at least require some words to actually prove the proof. And then you can also, so this is like one method, and then you can combine these methods to produce other tessellations. For example, this is one again by this guy, Al-Wafa. And this is, I'm actually not sure if this is like literally from what he wrote or if this is, I think it is Persian, but I'm not sure if it's like somebody else wrote it later, but in any case. So he was like, he was writing this book and he was writing about, he was at some group of artisans and they were talking about like, how can we dissect three squares to form one square? And you can't do it with the previous method because 3 is not the sum of squares, but you can do it by combining different methods. So you can take 2 of these squares, combine them to get one larger square, and then use the method from the previous slide to take any 2 unequal squares and make one square. So what it ends up being is this thing here, where essentially you first divide these into four right triangles, put them around the square, and then for every piece of the triangle, which is kind of like over the line where the square should be, you kind of like flip it over. And so it fills into this hole here, and this flips over and fills over here, and this flips over here, and so forth.
Sorry,
Mhm.
can I ask a question?
Yeah.
I'm not a math guy, but just out of curiosity, so when this guy invented this or discovered it,
Mhm.
was he starting with the visual representation and then deriving some equation, or was this stemmed from, like, was this an equation he wrote and thought up of and then visualized it?
I don't know. I think that I would guess it was a visual representation because I think that the connection between equations and these sort of geometric shapes didn't come around until, I think, like Descartes usually is given credit for that.
Okay.
So I would guess he started from like a Euclidean way of thinking where these are just like points and lines and angles and thought that way is my guess, but I don't know.
Okay.
Cool. Okay. Any questions about that? Okay, so that's kind of the tessellation method, and there's another. Hopefully, the next slide it is, which is a little bit more confusing, and so I'll read the words and then I'll show you what it means. I think it's kind of impossible to read the words, to like hear the words and understand it, but I think I'll do it anyway. So this is a strip method, which there are also variations of this method. And so this one involves you take each shape and you cut it into pieces that you can then arrange to fill out an infinite strip of constant width. So you've done that to both of the shapes that you want to you make a dissection between. Then you do what's called cross-posing those two strips. So you like take one at an angle and overlap it on the other one, so that either the area of the overlap, there's two conditions. Either the area of the overlap is the area of the shape you want to dissect, or the intersection points of the boundary lines on one are at as it says, a distance equal to the length of the elements of the other strip. And then again, you will let the line segments of one strip induce cuts in the pieces of the other. So, okay, so let's take a look at how this. So here's a problem. To dissect an equilateral triangle to a square. This is the same problem that was mentioned in the description that this guy Dudney had a solution for, but this is going to be a different solution. So what's going on here is, so here, for example, is the strip for the equilateral triangle. And so what's been done is we start with an equilateral triangle, but we need to make it into some element that's like kind of like infinitely repeating in one direction. So to do that, we chopped off the top of it and rotated it down here. And now we have a parallelogram and we can infinitely repeat this going off in either direction. The same thing we did with the square, except for the square was already, it was already the case that we could put it into a strip like this. We didn't need to do anything with it. And now what we have to do is we have to take this guy and turn it at some angle. There's like only one correct angle that you can turn this at. But you have to turn it at some angle so that this point, this point where this boundary intersects the strip, and this point where this boundary intersects the strip is exactly this distance apart. So for example, this angle is too shallow because this point and this point are way too far apart. And this is way too, well, it is too steep because these are too close. So you just kind of turn it at the right angle. And of course, if you want to make something exact, you have to actually figure out what the right angle is. You can't just eyeball it, but do that. Okay, so this is the right angle. And now you have like a choice. You can just like sort of move this, now that you have the right angle, you can just like move this strip around and you get different dissections. And you move it around until you get the dissection that you want. This like nicest. But say we like stopped it here for whatever reason, or maybe here. So what dissection does this correspond to, just to be a little bit explicit about it? Well, this part here, so the square, maybe I should draw something. So we have a square. This part here is dissected by this intersection. So this is something like this. This part of the square, this band here, is dissected by this part of the intersection. So it's something like this. This part is dissected by this. So it's like this. And I think that's it. I don't think I missed anything part. So that's the dissection of the square, and then you can similarly work backwards and move these pieces back around. So like, for example, we move this piece here, this piece here, this piece here, and you can reform one of these elements of the triangle, and then you just like flip this thing over and put the triangle back together. So this is a method to produce these things. It turns out to be a bit more flexible than the tessellation method. Are there any questions about
But
that? Yeah.
it's using a lot more than like the 4 pieces, which Dewdney.
Oh yeah. That's right. Yeah. So I'm not sure. I don't think you can get Dewdney's solution with this. You can get Dewdney's solution, and maybe we'll see it on the next slide. You can get Dewdney's solution with a variation of this. So this P strip thing is actually just kind of the start. There's other sorts of strips which have various other ways to flip things around that are more complicated but allow you to do get different dissections. And it might be like, definitely it's the best that I found, but like this guy, Gavin Theobald, who like has a website with, I don't know how many, but many dissections using the strip method. So let's take a look here. Let's see here. So yeah, so here's Dewdney's dissection using a variation of the strips. You can look around. It's actually like pretty complicated. So like here's like, some low numbers of sides, but like as you get higher and higher, they get pretty weird. Here's a weird one. This is fairly weird. So anyway, he has like a whole ton of dissections, and they're mostly variations of the strip method in some form. And the author of that book that I used cited this guy as, he's not, I actually don't know who he is, besides he has a website, but he's, I'm not sure who he is, but he's been cited in a book, so it must be real. Cool. Okay, so now let's turn from the recreational math to some more like regular math or more theoretical math. So before we were sort of concerned, or people were concerned with like finding the decomposition with the least number of pieces. But there is if you're not concerned with the number of pieces, there's a theorem from various people in the 1800s that you can always find some geometric decomposition from one polygon to another if they have the same area. So we observed before that they have to have the same area to do this, but in fact, as long as they have the same area, you can always find some decomposition from one to the other, which is good to know. And it's actually not too tricky a proof. You can kind of just go through it. And I'll tell you the proof steps, and then I'll go through it sort of again, so that hopefully it's clear. So basically the way that it works is you start out, you divide any polygon into triangles. So you do that. You then take all the triangles, decompose them into some rectangle. You then form a decomposition where you take that rectangle and you decompose it into any rectangle of the same area. Then that means that you can make it into a 1 by A rectangle, which I'll show a diagram for by stacking up all these other rectangles. And then once you do that, because these polygons have the same area, they can be decomposed into the same rectangle. So you can do this process with one polygon and then do the process in reverse for the other polygon. And then you'll get its dissection out at the end. So let's take a look at this. So the first step is to triangulate a polygon. So this means, to dissect it in some way so that it all becomes triangles. And I won't actually prove this fully, but I will indicate why it's true. So there is an algorithm. What you can do is, so you can start at any vertex, then look at the two vertices on its side. And it might be the case, as it is for the vertex which I just sort of pointed out, that the line between those two vertices is entirely within the polygon. In that case, you can say, okay, well, I'll just draw a line there. I cut off a triangle, and now I have a smaller polygon, so I can just cut off that triangle and then recurse onto this smaller polygon. So that's good. But that's not always what happens. For example, here, these two vertices that are next to that vertex, the line between them does not go through the polygon entirely. It kind of cuts out a hole in there. But it turns out that in that case, you can always instead find a line from the vertex you were considering to some other line closer in that forms the hole. And this again then cuts the polygon into two, and you can then recurse on those two polygons which you cut off. So for example, you make this cut, and you can then recurse on this one, and for example, you then do the same thing with that vertex, and you find this triangle, and you keep going. So that's why any polygon can be triangulated. So the next step is to show that any triangle can be decomposed into a rectangle. So that's, I think you can do this with some fanciness, but you can also just do it with like a sort of straightforward decomposition. So you can do this just by starting with any triangle and rotating it so its biggest side is on the sort of flat on the bottom. Then you can draw this, and it'll be entirely inside the triangle. And then bisect this line. And then you can kind of hinge this piece down here and hinge this piece down here and form a rectangle. And then the decomposition of any rectangle into any rectangle of the same area is actually really easy once you use p-strips. It's kind of actually like nothing to prove. Like you can just sort of do it. Like you can just take your p-strips and say, well, okay, here's my decomposition. I can decompose the square into this piece, this piece, this piece, and this piece. That's 4 pieces, and reassemble them to make this rectangle. And then you put it all together. So, as I said, so you do this one process. So you take this polygon, you triangulate it, you turn the triangles into rectangles, you turn the rectangles into rectangles of side 1, you stack them all up, So this is now 1 by the area. You do the same thing with the other polygon. You get a rectangle the same size because they're the same area, and you kind of go in reverse. And you undo that, and you come back to the initial polygon. So that's the proof. I was actually pretty surprised that you can or that I can understand that proof without too much difficulty. I thought it was going to be some complicated thing, but it turns out it's not so bad. Any questions about that? Cool. Okay, I'm actually not sure what's on the next slide, so let's find out together. Oh yeah, okay, so, right, so what is known about, okay, so we proved that it can be done with some number of pieces, but as my friend, not really my friend, this author, Greg Fredrickson, was said in this book, well, they really care about, a recreational mathematician who cares about puzzles really cares about minimizing the number of pieces and cares about maybe some aesthetic properties. We can't prove anything about that, but we can talk about the minimal number of pieces. The most surprising thing which I found in researching this is that it's really hard. It's really hard to prove anything. And in fact, that 4-piece dissection, which Dudney had of the triangle, that's not even known if that's the best. This is a paper that I saw in 2015, that was written in 2015, which remarked that it's not even known, you might be able to do that in 3 pieces. Nobody knows. And it's such simple shapes, which is very surprising to me. And the same paper, which by the way, I couldn't fit all the names of the people who wrote it, but I didn't want to give so here's the people who did it. Oh wait, let me undo that. Here's the people who did it. I couldn't fit all the names. And I also couldn't memorize them, so I can tell you. But it was a whole bunch of people. Okay. I'll assume you know all that. So what they showed is that it's hard. They remarked that finding the minimum number of pieces for our dissection is NP hard, which if you've heard of the traveling salesman problem or things like this, is at least as hard as that. And they also remarked that there's no known upper bound. It's not like it's in NP. It's that it's at least in NP, and it's unknown how hard it is. It might be undecidable.
Question, have they ever found for any figure the actual minimum number, or they never been done?
I never heard of that. I mean, of course, for trivial
Never
things, you
been
might
done.
know that, but
Never been done.
yeah, as far as I know, there's nothing that's non-trivial that I know. Yeah, I mean, I found that fairly surprising. It is known some asymptotic bounds. So a lower bound, so again, this was done by, there's a lot of collaboration in this field, I guess. This was done by these 3 people, who again, I couldn't, unfortunately did not memorize their names, but they should get credit. Who proved that it's, if you just sort of consider a regular polygon to regular polygon, and in fact, for stating the results, they consider a regular polygon to square. So if you take a square to an n-gon, you need at least n over 4 pieces. And asymptotically, you basically need n over 2 pieces. So they kind of have, restricted the range a bit between n over 4 and n over 2, which is okay. It's definitely more than I knew, but we definitely don't know exact numbers. It's difficult to find exact numbers.
N-gon are defined by the number of edges.
Yeah, or vertices, whichever. Okay, so the puzzling world does not stop with our foolish mathematical theorems. They march on and they do whatever they're going to do. So there's all sorts of weird puzzles involving curves and stuff like that. So here's one that's, again, from this book, where, you can't use your theorems about polygons now. This is some sort of curved thing where it's actually a circular arc and then a straight line and then a circular arc. And he's actually asking, so the puzzle is actually to take this thing and dissect it and make it into this cross, which is much less, obviously it has to be scaled up to be the same area, but this cross here. I'm not sure what the cultural context of a crescent cross is. Perhaps there was some, actually, I don't know. It turns out you can do with things like this. Oh, well, so one thing is, there is a solution to this in the book, which I couldn't understand. And also, the author points out that Sam Lloyd's solution was incorrect. So I won't try and give that one. But Hedry Dudney, who was Sam Lloyd's competitor, I think he was, they were partners and then they were competitors, offered his own thing, which is at least slightly more comprehensible. you can use the strip method. And so what's going on here is that you start with this crescent, and you kind of chop it in half, and then you use that to tile the this infinite strip. And then you tile the infinite strip in another way by making these cuts, which you just sort of know, you know you can do this, that this forms a cross. And then you take these pieces, so like for example, these cuts become these cuts, and these cuts flipped up become these cuts. And so now, this is again allowing pieces to be flipped over. So now you can, for example, take this and flip it over here. This goes here. This goes here, and so forth. So you can use the method we discussed before, even with curves, if you do it cleverly. But one thing to note here is that, which is kind of crucial, is that this area, this line is convex, and this boundary is concave, and they exactly cancel each other out. This sort of allows you to arrange things and you know, form a piece with like no convexity or concavity all around it. And in the 1920s, in 1925, Tarski wondered, what if you don't? He wondered, well, what if you had a circle, which of course is, I'm guessing you all know what a circle is. It's like convex all over. You know, it has this sort of outward curvature all over. He wondered, well, can that be decomposed into a square? It clearly can't be with straight cuts. But he was wondering, is there some like really strange cut that you could do and rearrange them to get a square? And this was shown, so like, if you're actually using cuts, so if your pieces are actually bounded by lines in the plane, then it was shown by these guys that no, you can't do it. The curvature argument doesn't really work because you might do really, really strange cuts that like are not differentiable and they don't have any definable curvature. But even with that, you can't do it. However, if you decide to leave the plane of you know, mere scissors and ascend to the abstract world of mathematical arbitrary sets, it turns out you can do it, which was proved in 1990. You need a mere 10 to the 50th pieces, and you have to invoke the axiom of choice. And so this invokes the axiom of choice. None of the pieces actually have a well-defined area. They're all sort of ephemeral clouds. Very practical. And in 2017, it turns out that with 10 to 200 pieces, you can do it with things which are still abstract, but they actually have an area. So you can assign each of these an area, and they're really weird, but you can rearrange them and come up with the square.
10 to the 200th shapes that have areas, but not really defined.
No, so these ones don't have areas. These ones do, but they're not. Their boundaries is not like, it's not a line. You know, it's something like the set of all rational numbers. You know, or all numbers with rational coordinates. They're things with a boundary. They're not simple. They're not simple things that are bounded by a line and everything into it. So.
I just, how can a piece not have an area?
If it has an open edge, or is not a closed boundary. So if a circle has, let's say, 1/4 of its bottom edge missing, that circle technically doesn't have a final area, because you can't bound the area at the bottom.
Yes, sir.
Well, the circle's cheating because the area is going to go pi r squared, but I'm like, but if it's also an arbitrary blob, it really can't if it's also open at the bottom.
There's a notion of Lebesgue measure which does assign an area to, or some measure to those things, and that's actually like what is generally referred to by area in this context. And so you're right. So it actually, like, it's not at all obvious that there are subsets of the plane that don't have areas. And I'm not prepared to, and it's not that I'm not prepared. I don't think I can reproduce the argument for why there can't be, or why there must be an area, a subset of the plane which has no area. But it turns out to be true. That like if you start with saying, okay, I want to assign a measure to subsets of the plane, it should have these properties, and you give some reasonable properties, it turns out that the reasonable properties which mathematicians picked mean that not every subset of the plane can be assigned an area. And these ones are weird enough so that they can't be. But with a few extra pieces, you can do it. And there's actually further work. In like this year, or sorry, in 2018, there was another decomposition with like even less weird pieces, but still very weird. But people are interested in this for reasons. Okay, and what if you wanted to allow pieces to be, so you say, okay, this translation rotation, that's too restrictive, it's too hard. What if I allow my pieces to be scaled instead? So now it turns out you can do it in 4 pieces. So here's this square, and so here's one piece, this blue thing, this, I don't know, brownish thing, this, well, the colors, I don't know, this purple thing, and this orangish thing. So here, so this blue thing kind of like fits, it has some sort of like fractal boundary and sort of like fits right around it. But the pieces are designed so that once you scale it down, it also fits right around this nub as well. And similarly, this orange thing has some little fractal boundary that's designed very carefully so that it fits around here, but also when you scale it up, it fits around the 2 of these things together. And same thing with this purple thing. So that if you allow yourself to scale these pieces, you can take 4 pieces and rearrange decompose the circle into the square. And these pieces have the nice property that, it's hard to cut them, but they are actually, they're pieces with one boundary and just everything is filled in from there. If you want to allow yourself to be a little bit more generous about what a piece means, you can do it with 2. So here is 2 pieces, this bluish green thing and this greenish blue thing. And so you imagine like this one piece, descends around all the way to the center infinitely. And then all you have to do is take this green thing and scale it up, and take this blue thing and scale it down, and they fit into each other again, and you've done it. You've made the square into the circle. So this is actually kind of what inspired me to do this talk in the first place. It turns out that it didn't really fit into this talk, but it turns out you can do this with essentially any 2 regions, not just the circle and square. There's a kind of an interesting argument that you can always make a decomposition like this. But it turned out not really. It's just like it's too hard to talk about. It's supposed to continue. It's supposed to keep continuing. It's like an infinite thing here where this keeps going on. Yeah, it's supposed to keep going. And I'm not sure this actually adds anything. Yeah. Cool. And it turns out that with a lot of these, like a lot of things that I've given talks on, actually, like you start doing research on this, and this like it just sort of branches out into like a bajillion different like really interesting things. And so for these last 3, so I'm actually going to I have 1 slide on each of these to kind of like hopefully give people a taste of like just like many other ways this can go, and then I'll kind of end it because there's like no real way to encompass this entire topic. A lot of the dissections we started by looking at actually didn't necessarily involve rotating the pieces. For example, the 5 squares to 1, that actually, you could actually do that thing by not rotating any of the triangles, but kind of moving them across the square. And there's a question as to whether or not you can always do that. For example, can a square be dissected in such a way to an equilateral triangle without rotating the pieces? I phrased it as a question, but I'll just tell you the answers now. Some dissections, and this is better with a picture. Actually, let me leave this one so I give you a picture. And then another direction is to ask the same question in 3 dimensions as to whether or not any 3D polyhedron or polytope can be dissected into any other one of the same, this should say volume. And the answer is no. This is true in 2 dimensions, but not true in 3. And this was posed by David Hilbert as a question like in 1900, and very soon after, his student Max Dane proved that you cannot do that. And I think, actually, so the thing about 3 dimensions is that there's more than one type of angle. In 2 dimensions, there's just one type of angle. There's like the angles on the faces, which you still have in 3 dimensions. But in 3 dimensions is another type, which is called dihedral angle, and that's the angle between faces. So for example, here, on this edge, the angle between these 2 faces is 90 degrees, and similarly for the other angles. And it turns out that there are like sort of properties of these angles that are kind of conserved when you make cuts in 3 dimensions. And so if you start with one type of polyhedron which has angles of a certain type, then you can't produce dihedral angles of that other type. And that property has to do with the rationality of those angles with respect to either pi or 180 degrees. And what Dane proved is actually, it's slightly complicated. He did give something which turns out to be a criterion for when you can dissect one polyhedron to another one. But a guy earlier named Bricard also gave a criterion for when you can do this. It turned out that he proved it incorrectly, but what he said was true. And so he's saying, okay, if you take all the dihedral angles, if you can find some linear combination of them with rational coefficients that comes up to pi, well, he said that's a necessary condition for your polytope being dissectable into a cube. And that just turns out to not be true for this tetrahedron. They all have the same dihedral angle, and the dihedral angle is like arc cosine of 3/4 or something like that. Actually, I'm not sure.
Oh, excuse me,
Mhm.
what polytope, I've never seen that word, what is it actually, what is a polytope?
So it's the analog of a polygon in, I think polytope is actually for any number of dimensions, and maybe polyhedron is for 3 dimensions. But it's the analog of a polygon in more dimensions. And maybe the easiest thing is to think about like a convex polygon. So like a convex polyhedron is just like you start with some number of points in 3 dimensions, and then just take all the kind of convex combinations of that. So you take all the points, which can be written as sublinear combination of those points, where the coefficient set of 1. Or so another way to think about it is you take all the points, you take some set of points in 3 dimensions, and you kind of like wrap a rubber sheet around it and let that rubber sheet be sort of stretched tight, and whatever that defines.
Doesn't have to be regular though?
No, it doesn't.
Doesn't have to be regular.
That's right, it doesn't. Yeah. These are both regular though.
Yeah.
Okay, so that's one further direction. Another one is this thing I mentioned about when can you do dissection that doesn't involve a rotation. And it turns out this was solved in the 1950s. The only reference that I could find was in German, so I couldn't actually verify this, but it says in this book, so I assume it's correct. And what this says is that you can do a translational dissection if, and I'll just read this, for every slope, the net movement around the boundaries of the polygon at that slope is the same or is equal. And so what this means is, suppose that we want to find a way to dissect this into this that doesn't involve rotations. Well, what you have to do is you first kind of walk around each polygon. So you, suppose we're walking around clockwise, both of them. It actually doesn't matter which way you go around as long as you go around in some consistent way. And then you look at every possible slope. So for example, say you're considering vertical slopes. So this square moves up 1 unit vertically and moves down 1 unit vertically. So it has a net movement of 0 vertically, and these things don't count. This triangle doesn't move at all vertically. So that also has a net movement of 0. So that works.
What about diagonals? They're kind of
Right, yeah, so that was one slope. You have to check that for every possible slope. So for example, if you check a diagonal like this has a movement of whatever the side length is here, something here, and this has 0. So that means it can't be done because there's one slope for which it failed. So there's no way to dissect a square into a triangle that doesn't involve rotations. And you can go back and look at the dissection we came up with, or the Dewdney dissection, and they all involve rotations because they must. And then the final kind of other strand of like further exploration that I kind of want is this idea of a hinged dissection. So this was done by these people. This is there's the same names from before, if anyone's paying very close attention. Some dissections, including the one by Dewdney, actually have the property that you can put little hinge points on some of the vertices, and then the dissection actually proceeds with all those points of contact being maintained, so that you can actually make a physical model where this sort of hinges outwards, flips around, and then folds back in to make the triangle. And these hinged dissections are considered, well, sometimes considered like more pleasing than other dissections. And people wondered, well, can you always make a hinged dissection? So if you have two polygons of equal areas, we know that you can come up with some dissection. Can you come up with a hinged dissection? And this was just proved in 2012. And it was proved that not only is that true, it was proved that any dissection you can possibly come up with can be tweaked a bit to become with a hinged one. And let me zoom in a bit on this diagram from their paper. So their example for this is, suppose that you have, so you've got this, you've got these shapes, and you want to turn to this shapes. So you want to move this guy up here. And this is for some decomposition that's like not hinged. So you're just kind of like moving shapes around. Well, how can you turn it into a hinged shape? Well, what you can do is like make a very tiny sliver of triangles all the way throughout here. And this allows this thing to fold, to move outwards, kind of like an accordion. This thing stretches out here. Then this thing flips around. All the orange things come in to fill in what was taken out of here. And then the things that came out of the green and blue triangles fill in what happened here. So you can affect this movement here in a totally hinged way. And this, you start from this idea, which is already, I wouldn't come up with it, and then you somehow generalize it to every possible dissection. And they did this in 2012, and it turns out that any dissection can be hinged. And that's what I found out. Turns out there's a lot of stuff to decompositions. Thanks. Let's talk about math.